Hi, I'm Professor Jones here talking about linear functions and slope from section 2.3. The objectives are to calculate a line slope, write the point slope form of the equation of a line, write and graph the slope-intercept form of the equation of a line, graph horizontal or vertical lines, recognize and use the general form of a line's equation, use intercepts to graph the general form of a line's equation, model data with linear functions, and make predictions. Let's start by defining slope. The slope of the line through the distinct points x1, y1 and x2, y2 is the change in y over the change in x. We call change in y the rise and change in x the run. And we calculate rise by finding the difference between the y values. We calculate run by finding the difference in the x values, making sure that the x that comes first in the difference in the x values corresponds to the y that came first when we calculated the difference in the y values. And to calculate slope, x2 minus x1 cannot equal 0. If it does, our line is vertical and the slope is undefined because division, we would be dividing by 0 if x2 minus x1 were 0, and division by 0 is undefined. Let's look at an example using the definition of slope. Find the slope of the line passing through the points 4, -2 and -1, 5. So we begin with our slope formula. We calculate the change in y over the change in x, which is the same as saying calculate rise over run. So 5 is the y-coordinate we use first in our calculation of rise. So we have to make sure the x that corresponds to 5, -1, is first in our calculation of run. So 7 over -5 is our result. And that's the same as -7 over 5. And I just want to point out that when a fraction is negative, you have 3 positions you can put the negative sign in. You can either put the negative in the denominator, level with the fraction bar, or in the numerator. Please note that these are all equivalent. The point slope form of the equation of a line that is not vertical with slope m that passes through the point x1, y1 is y minus y1 equals m times x minus x1. So let's look at an example of writing an equation in point slope form. So our line has slope 6 and passes through the point 2, -5. So then we'll solve the equation for y. So here's our point slope formula, and our y1 is -5, and our x1 is 2, and our m is 6. So we'll make those replacements. Let's simplify y minus -5 to y plus 5. So notice that we were asked to find the equation in point slope form. And so now at this stage, we've actually found the point slope form of the line equation. So notice we don't apply the distributive property or isolate the y when we leave the equation in this form. We are, however, asked to go on and solve the equation for y. So now we will use the distributive property. The slope 6 times the quantity x minus 2 gives us 6x minus 12. And let's subtract 5 from both sides of the equation. And we find out that solving the equation for y gives us y equals 6x minus 17. And notice that this is actually the slope-intercept form of the equation. So the slope-intercept form of the equation of a non-vertical line with slope m and y-intercept b is y equals slope times x plus the y-intercept. Or in other words, y equals mx plus b. So when I want to graph using the slope and y-intercept form of the line equation, I begin by plotting the point that is the y-intercept on the y-axis. So this is the point 0b. To be on the y-axis, your x-coordinate has to be 0. Then I obtain a second point using the slope m. I write m as a fraction and use rise over run, starting at the point containing the y-intercept to plot this point. Then I use the straight edge to draw a line through the 2 points. I draw arrowheads at the ends of the line to show that the line continues indefinitely in both directions. So let's look at an example of graphing the linear function f of x equals 3/5 x plus 1. Remember, f of x is the same as y. So step 1 is to plot the point containing the y-intercept on the y-axis. So the y-intercept is 1. So this point that we're going to plot is the point 0, 1. So we plot that on the y-axis. Step 2 is to obtain a second point using the slope m. If the slope is not a fraction, we would make sure to write it as a fraction and then use rise over run graphically, starting at the point containing the y-intercept to plot this second point. So we already have the y-intercept plotted, and then the slope is 3/5, so the rise is the numerator of the slope, and that is 3. So from the y-intercept, we're going to rise, and in this case, we're going up because the rise is positive. A positive rise means move up. A negative rise means move down. The important thing to note is that I'm starting from the y-intercept, and I'm moving in the positive direction 3 units. Now I'm going to use the fact that the run is 5. So from the location that I arrived at after implementing the rise, I now implement the run, which is 5. And I move 5 units in the positive horizontal direction. So when run is positive, I move to the right. So I move 5 units to the right. And that actually positions me at a second point on the line. Now I'm able to plot that point, and I see that the point is the point whose x-coordinate is 5 and whose y-coordinate is 4. So we're able to plot the point 5, 4. So this point has an x-coordinate of 5, a y-coordinate of 4. And now we can draw the line through these 2 points. To draw a line, I only need 2 points. And there is the graph of the linear equation. The equation of a horizontal line is in the form y equal b, where b is the y-intercept of the line. The slope of a horizontal line is 0. So y equals mx plus b becomes y equals 0 times x plus b, which becomes y equals 0 plus b, which is simply y equal b. The equation of a vertical line is given by the form x equal a. A is the x-intercept of the line. And keep in mind, as we said earlier, the slope of a vertical line is undefined. So let's look at an example of graphing a horizontal line. Let's graph the line y equals 3. Well, essentially, as we said a moment ago, 3 is the y-intercept of this horizontal line. So horizontally, we draw a line through the point 0, 3. It's as simple as that. Another form of the equation of a line is the general form. Every line has an equation that can be written in the general form. And that form is ax plus by plus c equals 0. A, b, and c are real numbers, and a and b are not both 0. So let's look at an example of finding the slope and y-intercept of the line whose equation is 3x plus 6y minus 12 equals 0. Note that this is the general form of our line equation. So we begin by isolating y. So our first steps in isolating y is to add 12 to both sides of the equation and to subtract 3x from both sides of the equation. So we're now left with 6y equal negative 3x plus 12. And to isolate y, we need to divide by 6. But each term gets divided by 6. Simplifying this, y is equal to negative 1/2 x plus 2. So the slope is negative 1/2. The y-intercept is 2. We can also, with the general form, use intercepts to graph the equation, as long as the line is not a vertical line and it's also not a horizontal line. So to do this, we find the x-intercept. We let y equal 0 and solve for x. And then we plot the point that is the x-intercept on the x-axis. Then we find the y-intercept. We let x equal 0 and solve for y. We plot the point containing the y-intercept on the y-axis. We use a straight edge to draw a line through the points containing the intercepts. Draw arrowheads at the ends of the line to show that the line continues indefinitely in both directions. So let's look at an example of using intercepts to graph a linear equation given in general form. 3x minus 2y minus 6 equals 0 is our equation. First step is to find the x-intercept. We do that by letting y equal 0 and solving for x. So 3x minus 2 times 0 minus 6 equals 0. That means 3x minus 6 is 0. If we add 6 to both sides, 3x is 6. Now let's divide both sides of the equation by 3 to obtain x equals 2. So the x-intercept is 2. So the line passes through the point 2, 0. Step 2 involves finding the y-intercept, and we do this by letting x equal 0 and solving for y. So we're going to replace x with 0, and we obtain negative 2y minus 6 equals 0. Let's add 6 to both sides to get negative 2y equals 6. Now let's divide both sides of the equation by negative 2 to get y equals negative 3. The y-intercept is negative 3, so the line passes through 0, negative 3. Now the third step is to graph the equation by drawing a line through the 2 points containing the intercepts. So the y-intercept was negative 3. The x-intercept was 2. We plot the points that are the intercepts, and then we draw a line through those 2 points. And that is the graph of our line. The last thing we want to do here is look at an application. And this application is one where we have 2 data points, and we are asked to use these 2 points to obtain a linear function that models average global temperature, f of x. So that means our y values represent average global temperatures for an atmospheric carbon dioxide concentration of x parts per million. And we want to round m to 3 decimal places and b to 1 decimal place. So x then is my atmospheric carbon dioxide concentration, and it's given in parts per million. So our slope formula, as we recall, tells us to calculate rise over run. So we find the difference or the change in y, and when we find the change in x, 57.64 was the y value that came first in the calculation of rise. So we have to make sure the corresponding x, 354, comes first in the calculation of run. So we find out that rise is 0.60, run is 37. If we round that to 3 decimal places, we get approximately 0.016. Now, to find the equation of the line, we're going to use the point-slope form of the equation, since we have a point and the slope. So y minus 57.64 is our slope, 0.016, times the quantity x minus 354. We'll use the distributive property on the right side. And now let's add 57.64 to both sides of the equation. So this then gives us a linear model of this application. So the linear function f of x is 0.016x plus, and we were told to round the y-intercept to 1 decimal point, so 51.976 rounds to 52.0. So this is the model of average global temperature, f of x, for an atmospheric carbon dioxide concentration of x parts per million.